Okay, going forward, we're going to be talking about properties of trigonometric ratios, and specific the exact values properties. So we're going to find the exact values of trigonometric functions of multiples of 30 and 45, and then we're going to identify and use these theorems relating sine, cosine, and tangents. So knowing we're doing that, let's move ahead and say, here's a few new things. There's something called the complement theorem. When you have the sine of any angle theta, it has to be equal to the cosine of 90. Now, just grab your calculator as an example here. And if I would ask you to do the sine of 15 degrees, and you would go to your calculator, again, make sure it's in degree mode, and if you did the sine of 15, you should be looking at about a 0.2588-ish. But according to that, if we take the sine of 15 and we look up here, then that should be equal to the cosine of 90 minus theta. Well, that would be complement. Complement from geometry said two angles that add up to be 90. So 15, and just do a quick subtraction is the easiest way. So 90 take away 10 is 80, take away 5, 75. So we should have a 75. Now go to your calculator and this time hit cosine of 75, and it should be that identical 0.2588-ish number. So that's going to be true for all acute angles. The sine of any angle theta is equal to the cosine of its complement, is how we say that. And if I turn it around, the cosine of any angle is equal to the sine of its complement. So we should be able to travel anywhere between 0 and 90 and come up with lots of our sine, cosine values that would be practical and usable. Then, again, we could show you a theorem, or a proof, sorry, for the theorem. But if you just picked a value again, and we started with 15, so maybe let's go with it. If I said, take the cosine of 15 degrees, find out what that is, go ahead and square it, add that to the sine of 15 squared, you should get 1. Every single time. And again, this is the acute angles that we're talking about. That's what we're worried about right now, all of our angles that are still in our triangles. And then there's one more that's interesting. The tangent theorem, which is what we like to call this one. I don't have the name up here, so let's just go tangent theorem, abbreviate it, tangent theorem. Is nothing more than the tangent of any angle is equal to its sine over its cosine. So while we're going good with 15, and it doesn't just work with 15, but if we're going with it, let's go the sine of 15 degrees divided by the cosine of 15 degrees. Hit enter, and then see that decimal, and then now do the tangent of 15 degrees, and you should see that both those decimals are equivalent. So these are 3 different shortcuts that you should be able to use. Complement, Pythagorean identity, which looks like a lot like a squared, b squared, c squared. Think of it that way. And then you've got your tangent theorem also. And we're going to show you how you're going to use those as we move forward. Okay, but we need to, as I say, memorize these. They're shortcuts. You use your calculator on any angle that's not easy. When we say easy, we're going to characterize that as we move forward too. Easy. You were in geometry and you spent quite a bit of time discussing 45, 45, 90 triangles and also 30, 60, 90. We call them special right triangles. A 45, 45, 90 is set up similar to this, and you were expected to do the math if we said, hey, find that missing edge. And so you said, well, wait a minute, that's Pythagorean theorem because it's a right triangle. A squared plus b squared equals c squared. So see if this brings back some memories, and if not, jot it down in your notes. A squared, b squared, c squared, the two short sides of a right triangle squared should be added together, and they should equal the hypotenuse squared, the longest side. So in this case, we have x squared plus x squared has to equal c squared, which is our unknown, we'll call it right now. And I had it marked, so we'll call that C. And from there, if we do that, we can add those x squareds. That's 2x squared. But we know we don't want c squared, we want c. So if we take the square root of both sides, we would end up with the square root of 2x squared. And we know that x squared is a perfect square, so it would come out, and we'd have x root 2 equals c. So what that basically tells you, and you don't have to do this every time, we do it once and we're done. If we have our two edges that are, now I do have to move it to get the x back where it belongs. If we have our two edges which represent equal lengths, then we'll always have x times the square root of 2 on that opposite side. So you should have learned x and x are the sides opposite the 45, and x root 2 is always across from the 90 in a 45, 45, 90 triangle. Okay? Should sound familiar. We're going to talk about edge length shortly. But let's go to the other one, the 30, 60, 90. You should really have been taught that a 30, 60, 90 really comes from 3 60s, the equilateral. If we cut it in half by our perpendicular bisector, we now have two 30, 60, 90s. And so, thinking-wise, if we would have called this side H for our unknown edge, we don't know what it was, they were all H's. But if this now has been cut in half, it would be half of H in each spot. And half of H and half of H adds up to 1H. So if we just look at the triangle in black, then we have a 30, 60, 90, and we have two of the edges again. But based on what we just showed you, you could use that complement theorem. So the sine of 30 has to equal the cosine of 60, and the sine of 60 has to equal the cosine of 30. That'll definitely work. But again, the question is, what happened to this third edge? We should be able to get it. Pythagorean theorem, similar like we did on the last one. It should look like this. And in doing so again, so quickly, we would take the 3, a squared, b squared, c squared, Pythagorean theorem, take the two edges we know, the 1/2 h, and the hypotenuse h, and it's the b this time that we don't know, and we do the math, we square what we know, we combine the like terms, so we end up with b squared equals 3/4 h squared, take the square root of both sides, and we can simplify, and we have in this case that third and final edge being square root of 3 over 2. Now if you look at this, square root of 3 over 2 is not a really nice number, and actually some of you who don't like fractions found a quick and easy way to get rid of all these, and that was to double them. If you doubled 1/2 h, doubled, and just made it a bigger triangle, in other words, that's all there is, then you ended up something with edges like this. So we don't care which edge length you have memorized, whether it's h, 1/2 h, and square root of 3 over 2h. We don't care if it's that, or, for those of you who don't like fractions, x, 2x, and x root 3. But what we do care about is that you have memorized where they're at. And again, still in our picture, that's our 60, that's our 90, and that's our 30. So you should have memorized across from the 90 is always 2x, the longest edge. Across from the 30 is half of that, or x. And across from the 60 is x times the square root of 3. And some people like to remember it's next to the 30 where the 3 is at. It's fine. Whatever works, because that's what you have to keep working on. That's what we expect to have memorized for 30, 60, 90. That you can name those edges very quickly. Okay, so knowing that, x was across the 30, 2x across in the 90, and x root 3 is across from the 60. We're going to go right into find the missing parts. Well, you've got to look at this and say, well, wait a minute, there's a missing angle right away. And if we talk about missing angles, we could fill that in, no problem. Arithmetic says this has to be a 30, 60, 90. But now we have two edges that we've got problems on. Oh, so if the longest edge, hypotenuse is 18. We said opposite the 30 was half of that, so that's a 9. We said opposite the 60 was x times the square root of 3. Well, if x was 9, then this edge has to be 9 root 3. And we didn't do any more math. We didn't have to do Pythagorean. We just knew that relationship because it happens on all 30, 60, 90s, and we can fill in our edges very quickly. You should be able to do that in some of your problems today. So if we did the same thing, and we looked at this triangle, the only problem with this one is I forgot some measurements. So if I did that from geometry, your skills are telling you that, oh yeah, those are equal edges. So immediately you then know we have a 45, 45, 90. The 90 is already marked. All right. So if you start looking at that, well, wait, that's the hypotenuse in a right triangle that's 45, 45, 90. And we learned that it's x, x, and x times the square root of 2. So that long edge is really that x root 2 value. Well, let's just set it equal to what it is and solve for x. So right now we know that the length opposite the hypotenuse is x times the square root of 2. We also know it's 5. They have to be equal. So let's divide both sides by the square root of 2. And we'll actually have that value. But we want to make sure, as most of you know, that it's in the right form. And currently that does not look like the right form because we have a radical in the denominator. So we need to rationalize that denominator. And we do that by multiplying by that fancy form of 1. And that fancy form of 1 puts us at, 5 root 2 up on top, all over the whole number 2. And so 5 root 2 all over 2, final answer, and that would be our edge for both of these because it's a 45, 45, 90. And that's your exact edge. We don't want to go into a calculator, punch that in, and find in the messiness. These are exact values, and that's what we're looking for in this section. So what we're now asking is that you should memorize, and again, from geometry, that we can get all our combinations from just 3 possibilities, and we'll talk about that right here. Notice that they go in order, 30, 45, 60, and we're only dealing with sign. And then the best way to think of it is start looking. They're all divided by 2, so that's a nice part. And then I like to say if you've got them in order here, 30, 45, 60, you've got them in order here, 1, 2, 3. And when I talk to people about memorizing it, then you say, okay, I know they're all over 2. I know they're all over 2. And then you just start putting square roots in and you start counting. But then most of you will eventually learn that the square root of 1 really is just 1. And so that's why we have 1/2 square root of 2 over 2 and square root of 3 over 2 as our 3 values that represent sine of 30, 45, and 60. Those are going to be crucial because those are the only angles you really talked about in special triangles last year. They were either 30, 60, 90, or 45, 45, 90. Now, the last thing is, if I say, hey, what's the cosine of 60? Your brain has to say, wait a minute, she taught me today that cosine of 60 is equal to the sine of its complement. Well, that'd be the sine of 30. Well, that means cosine of 60 has to be equal to the sine of 30, and we just did the sine of 30 is 1/2. So I know that the cosine of 60 is also 1/2. You should be able to bounce back and forth on exact values like this. So if I ask, what's the cosine of 30? Oh, cosine of 30 is the same as the sine of 60. Sine of 60 is square root of 3 over 2. Done. Now if I ask tangent, and tangent of 45 is probably one of the easier ones, but tangent we learned today was just nothing more than the sine, and I was going to put theta, sine of 45 over the cosine of 45. Well, wait a minute. You have both of those in your exact values. The sine of 45 is square root of 2 over 2. The cosine of 45 is the complement. Oh, so we got square root of 2 over 2 Square root of 2 over 2. What is anything when you divide it by itself? And the answer is a big fat 1. And so the tangent of 45 does equal 1. Now you'll do something similar to that for the tangent of 60 and the tangent of 30, but you will have to do a little division. They will be fractions. They will not be nice whole numbers like that one. So work on those, memorize them. We got to get better and faster throughout this chapter using sine, 30, 45, 60, because you'll be expected to know them when you move on to FST next year and in the future. Okay. So that ends our discussion today. Bring any questions you might have to class for further discussion.